Let's understand the question. The number of 5-digit numbers, the sum of whose digits leaves a remainder of 2 when divided by 4. Not the required number leaving a remainder. What is the number which should leave a remainder? The sum of its digits should leave a remainder 2 when we divide the sum by 4, right? Now let's consider how do we create a term whose sum of the digits is taken into consideration. Yes, for that let us consider this expansion. T plus t square plus t cube plus t to the power of 4 so on up to t to the power of 9 into 1 plus t square plus t cube so on up to t to the power of 9 whole to the power of 4. How will be this expansion? Yes, the minimum power would be 1 and the highest power would be 9 plus 36, that is 45. So these terms would be in the form b1 into t plus b2 into t square plus b3 into t cube so on up to this sum would be up to b45 times t to the power of 45. Now here the important observation is the value of bk, where k runs from 1 to 45, is the number of 5-digit numbers. 1 digit coming from the first bracket where 0 is not included at the 10,000s place, and the rest coming from the remaining 4 positions, thousands, hundreds, tens and units. Then the total number of 5-digit numbers whose sum of digits is k, right, where k runs from 1 to 45. Now what is required from this now? We need only those bk's which leaves a remainder 2 when divided by 4. That means what are we looking at? Therefore, the required number is the sum of all those numbers which leave a remainder 2. Yes, those numbers which leaves a remainder 2, that is b2, b6, b10, b14, so on up to what would be the last power up to 45? Yes, it would be b42, which also leaves a remainder 2 when divided by 4. Now we need to find this sum, right? Let's proceed how to find this sum. If we call this equation as 1, in the equation 1, let's put t equal to 1. What will happen to this equation? Yes, this side it will be 1 plus 1 added 9 times. So it is 9 into, how much would be the terms here? There will be 10 such terms. So 10 raised to the power 4 is, what would happen when we put t equal to 1 here? We get b1 plus b2 plus b3 plus b4 so on up to b45. Now let's call this as equation 2 with us. Now in the same equation 1, let's also put t equal to minus 1. When we put t equal to minus 1, then this factor becomes 0 and therefore the total product becomes 0 on the left hand side, and 0 equal to, when we are putting t equal to minus 1, alternate terms become minus. When there is an odd power, the term remains minus 1. Then it is minus b1 plus b2 minus b3 plus b4 so on up to the last factor would be minus b45. Let's call this an equation 3. Now if you look at 1 and 2 and 3, b1 is a plus term in the second equation, but b1 is with a minus sign in the second equation. So when we add the two equations 2 and 3, yes, what do we get? b1 cancels, b3 cancels, all the odd terms gets cancelled, leaving us with 2 times b2 plus b4 plus b6 plus b8 plus so on up to maximum term that remains is b44. All the even powers remain is 9 into 10 to the power of 4, right? So can we separate the value of b2 plus b4 plus b6 plus b8, sum of all the even coefficients is up to b44 is, when we bring the 2 to this side, it cancels with 1 of the 10 here and leaves us with 45 into 10 cube. Now let's call this as an equation 4. But if you look at what we require, this is also sum of even terms, but not all the even terms. Those even terms which leave a remainder 2. That means still this b4, b8 which are multiples of 4 are excess in this. So how do we remove this b4, b8 excess terms here? Yes, let's again consider equation 1 and put x equal to I in the given equation and equate the real parts on both the sides. What do we get by equating the real parts on both the sides? When we put x equal to I in this equation 1 here, yes, some of these powers would become 0. So the left hand side becomes 0. And how would be the right hand side now? With only the real part collected, where the terms are I, we reject them. Then B2 remains plus B4 because I to the power of 4 is plus 1. Minus B6 because I to the power of 6 is minus 1 plus B8 I to the power of 8 is 1. So alternate plus or minus terms would be remaining up to maximum of plus B44. Now when the power is a multiple of 4, I would give us plus 1, and when the power is a number which leaves a remainder 2 by dividing by 4, we'll be having minus 1 in there. So when we equate the real parts, this would now become the fourth equation. And recollect what is equation 4 with us? B2 plus B4 plus B6 so on up to B44, all even basis sum is 45 into 10 cube. This would be our equation 5. Now what happens when we again add 4 and 5 equations? Now this equation, can we rewrite this as separating all the minus terms to one side? Can we write B2 plus B6 plus B10 plus so on, where the reminders are leaving a remainder 2 by dividing by 4, that is B42 is equal to the other coefficients which are having plus sign, that is B4 plus B8 plus B12 plus, these are the coefficients which has multiples of 4, then it is up to B44. Now this is our equation 5. Now what happens when we combine the results which we got in 5 and 4? Yes, the total sum of all the even coefficients is, that is B2 plus B4 plus B6 plus B8 plus B10 plus so on up to B44. Sum of all the even coefficients is obtained as 45 into 10 cube. But in the from 5 equation, the alternate term sum is equal to the remaining alternate sum. So can we write 2 times the required sum B2 plus B6 plus B10 plus so on up to B42 will be equal to 45 into 10 cube, right? Then what is the value of the sum of those numbers which are leaving a remainder 2 when divided by 4? Yes, this is 45 into 10 cube by 2, which is nothing but 45,000 by 2, that is 22,500. So what are those numbers whose sum of the digits is leaving a remainder 2 when divided by 4? Yes, there are 22,500 numbers which leaves a remainder, whose sum of the digits leaves a remainder 2 when divided by 4, right? A very important application of multinomial theorem in the form of finding the required sum B2 plus B6 plus so on up to B42, right?